All right. I'll start.
Yeah.
Oh, so
Yep, go ahead. Yeah, I was
right.
distant because the microphone was coming through the other machine, so that's no problem.
Okay. Okay. Cool. All right. I'll start. So our goal is to prove main formula 2, and this is main formula 2. Given a truth density, a model parameterized by W and a prior on the parameter space, we have the following definition. So F throughout this talk will be equal to the log likelihood ratio, which is log of the ratio between the truth and the model. And Kn of W is the empirical version of the K function, the average, the expected likelihood ratio that we'll be mainly studying, which is just the empirical average of over the data set of F. And our normalized evidence, or the normalized partition function, or the normalized marginal likelihood, there's many names for this thing. It's kind of the main quantity we are interested in, which and we have introduced this before, and it's equal to either negative n Kn of W and integrate over the prior throughout the parameter space. And our free energy, or in this case, the normalized free energy, is negative log of the normalized evidence. And our goal is to prove the following asymptotic expansion, which says that the free energy is equal to lambda log n times n minus 1 log n term, and plus a random variable. And this sequence of random variable converges in distribution to a random variable. So this is saying that this term here is order 1, but it's an order 1 in terms of random variable, and that means a sequence of random variable is order fn for some for some function of n f, if and only if when you divide it by fn, it's bounded above by a, in ordinary asymptotics, it's bounded above by a constant, but this is bounded above by a random variable, where c is a random variable. All right, so that's our goal here, and we are going to state this a lot more carefully in a bit. So previously, we have proven main formula 1, which will be our last ingredient needed to prove main formula 2. And main formula 1 says that there exists a resolution map G, and throughout G is going to be the resolution map of such that we reparameterize W epsilon, which is the set where K is less than or equal to epsilon for some epsilon. And we reparameterize that set with a real analytic manifold M, such that in every local chart U of M, we can factorize the function f like that. AXU is a real analytic function of U, and KG of U is normal crossing, and we can define this variable, which is the difference between Kn and its mean. So if you normalize it properly outside of the zero set of K, this is going to be converging to a normal distribution, but it is not well defined near the zero set of K, which is why we need to resolve it. And once we resolve this using G, then this quantity is defined on O of n. Right, and we have proven this property, which is this process has mean 0 by construction, and its correlation function is given by expectation over just the x of the AXU function we have defined above. And we haven't quite proven this. In fact, there's a lot of convergence of random variable that we haven't proven, but and that requires some background in weak convergence of measures, and so on. So we're just going to take it as fact that this sequence of random variable converge to a Gaussian process on M. So this is like a function space version of central limit theorem. Okay, let's move over to the second board. Just to recall that to prove main formula 1, we needed a few conditions, and this is called for the fundamental conditions 1 in the gray book. And I'm going to review this because we're going to use main formula 1 to prove main formula 2. These conditions are assumed as well, and they are going to be upgraded in a moment. So in fundamental condition 1, we assume that our parameter space is a compact set of R to the D. So this is a schematic picture here. So R to the D is represented by a line, and W is a compact set of that line. I draw here as if this W is has non-empty interior, but I'm not sure if it is needed in main formula 1. But it is certainly needed in main formula 2. Right, but the point is somewhat moot when we look at other conditions. So if W naught is our zero set of K there, and the second the second condition says that the f function extends to a holomorphic function on a larger set. Well, a holomorphic function is defined on an open domain, and it's holomorphic and it's complex, and that means that we are talking about complex domain at the moment. So that's a little bit weird. So it's saying that function f of x can be extended. So meaning in the Taylor series, in the power series expansion of f, you can put in complex variable and it still makes sense. So it's extending it to c to the d, and we call that set w to the c, and it's an open set. Right. I should say that there is also a corresponding w to the r that contains this real analytic set, and w to the c contains w to the r. Right. The same picture happens near when we localize near the zero set. So basically, there is a w epsilon like that, and contained in a w to the r epsilon, which is itself contained in a w to the c epsilon. Okay. Right. So that's the condition on f, and we needed kw, that expected log likelihood ratio, to be real analytic because we are going to apply resolution on singularity to this function. And w naught, its zero set, is assumed to be non-empty. And that's the realizability assumption here. I think in the future we are going to discuss how to extend this to the unrealizable case. Right, and there's this technical condition which is just needed for the convergence of the Cn variable. This is needed to prove that the variance of Cn on the zero set is constant. Right. Okay, so that's what we have, what we needed to prove main formula 1, and main formula is going to be an ingredient for our proof today, and the other ingredient is the series of bounds on something that we have been looking at, which are a series of singular integrals, and I'm going to remind us of what those are. So so singular integral, and we have bounds for them that we have proven previously. So we have investigated something called a partition function, which is just defined as follow. So that n of C and Phi are both bounded Smith functions. And Phi is greater than 0. And that was defined to be 0 m. So we call that x. We partition our set of coordinates into two parts. One part, the x part, is what we will call the essential ones, and the y are the non-essential ones. The essential ones essentially means that in the following writing, x to the 2k, y to the 2k prime, the essential one essentially means that that there is a lambda which is equal to h I minus 1 over 2ki, and that is a constant. That equality holds for a constant lambda for all I from 1 to m for all the essential coordinates, and the non-essential ones have this quantity larger than lambda. So let me index them with j, and those are the prime coordinates and correspond to the y's. For j equal to 1 to s, and m plus s is equal to our dimension here. All right, and we had a bound for this, which is saying that it is its leading order is equal to some constants times log n. Its leading term is the following, and its leading order is log n to the n minus 1 over n to the lambda. Okay. By the way, throughout, this norm is going to be the supremum norm. So over the domain of the function. And mean of phi. So we have this sandwich inequality for this singular integral. Okay, I'm running out of phase space. So that is also, sorry, I mean z is less than or equal to some other constant with the same leading behavior times a different constant. Okay, so let's talk about how we are going to how we plan to use this couple of ingredients. So let's move to the next board. Okay, the plan. The plan is to use main theorem 1, so that in every local chart in every local chart that intersects the zero set, we can So in main formula 1, we have the coordinate u, right? And we are going to rearrange them so that we can rearrange them into the essential and non-essential, where the essential one satisfies the condition above about their the hi plus 1 over 2k, right? And then in those local charts we have k composed with the resolution give us x to the 2k, y to the 2k prime, and phi composed with the chart give us and multiplied by the Jacobian of the chart is equal to phi of xy, x to the h, y to the h prime. And this phi function is going to be bounded away from 0 and smooth. And then we have the quantity that we needed to evaluate our partition function, our free energy, which is Kn. So when that is composed with G, we get x to the 2k, y to the 2k prime, minus 1 on root n, x to the k, y to the k prime, and xy. Right. So so Zn naught, the thing that we want to evaluate, can now be represented as using a partition of unity. The integral of our normalized evidence can be represented as a sum over local charts, m alpha are local charts in M, of e to the n. And so it's an integration where it's equal to e to the n times this quantity, and we are going to substitute. So n beta kn composed with g of xy, right? That's the quantity that we want. So that looks like m beta multiplied by 2k y to the 2k prime minus m beta multiplied by the second term, which gives us beta root n x to the k y to the k prime cn of xy. And then we have the prior, which after composed with the resolution, we get that. So together with the Jacobian. So that's the integral that we are going to investigate now. Another crucial point is that we can cover our manifold M by a finite number of charts because of compactness. So this is a finite sum. So alpha is a finite index, right? Sorry, and I forgot our partition of unity. There is a sigma alpha of xy in here. So that's our partition of unity. So that's greater than 0 and smooth. Okay, so we want to use our bounds on integral like that. So our task is to see whether or not this is equal to the same finite sum over our integral, our singular integral before, where we substituted, where we just pattern match, and it's equal to Cn and multiplied by phi. And then we seek bounds on that. So if we have this, let me go to the next board. If we can justify that, and we can continue with the following, but this is going to be a sloppy proof to illustrate the idea. The idea is that if we have that representation in every local coordinates, we can separate out the Zn's integral that achieve some highest order behavior. And we are going to call those essential coordinates, and record the bound on this singular integral, and they are equal to something of this form, n to the lambda, times some remainder, which let me index by the charts, plus the remaining charts, which have different leading order behavior. And we will factor out this log n minus 1, n to the lambda, and that gives us, so the first term just become one big sum. So that is constant independent of the chart. That multiplicative term is independent of the chart. Plus, well, so this thing, after factoring out the leading order, we get log n to the m alpha minus m over n to the lambda alpha minus lambda r alpha n. So the claim that that the essential charts have leading order behavior just means that this thing converged. So decay to 0, meaning either lambda is greater than lambda alpha for all alpha, or if they are equal, we need m to be greater than m alpha. Sorry. So either lambda is smaller than lambda alpha for all alpha, or we need m to be bigger than m alpha for all alpha. Right. For this convergence to whole. Right. And then we will take negative log of the expression above. That's equal to lambda log n minus m minus 1 log n plus I'm going to factor out the Rn's here, which gives us negative log of Rn plus negative log of 1 plus, well, something that decays to 0, improbability, because these are because of this effect here. Well, so this is going to be, so we need to prove that this term is actually order 1, and we are going to prove that this term is is of order less than 1, but actually we were going to prove that this is of order log 1 on log n. So the worst behavior here is just that lambda is equal to lambda alpha, and then m is m is greater than m alpha, but only by 1. Right. So our to do is to so isolate essential terms, so highest order terms. The second thing is we need to justify this this partition of partition of the parameter space into integrals of the form that we have bounds for, which is justified in the M of R charts, we can have charts that is equal to the partition into essential and non-essential coordinates that we want. And then we need to show that remaining term is OP1. Okay, so that's all to do. All right, prepare for lots of calculation. Moving back to the first board. Okay, so we will start with theorem 4.9 of the gray book. So the purpose of this theorem is isolate essential part, not for all charts, but just for each singular integral. Right. So the theorem says that if we have C phi smooth function and phi is greater than 0, actually it only needed to be C1, but let's assume more here. Then we can define y of nc phi to be equal to the following complicated expression, but the idea is that it is kind of the central part of the z of the singular integral here. So it's equal to some constant times leading order behavior. By the way, m and lambda has the same interpretation throughout in terms of the exponents of x to the k and x to the 2k prime, and x to the h and y to the h prime. So the k's, k prime, h, and h prime multi-indices are all given as for a particular partition function. So that's equal to this integral. Okay, but what phi naught, where phi naught, c naught, sorry, where c naught of y is defined to be c of 0, y, and phi naught of y is the same. So we zero out the essential coordinates, which is same as looking near the zero set, but then okay, I'm not too sure about the interpretation here. So, but we are definitely looking near the zero set. But then we want to integrate out the y coordinates, the non-essential ones. Okay. So then the theorem says that the partition function the theorem says that y hold the leading order behavior for the partition function. So then there exists a constant c greater than 0, such that this is this is bounded above by, and this is the crucial part, this is bounded above by m minus 2. So it's one order smaller. So one order of logs smaller. Okay, the constant term here is going to be complicated, and that's because of how the proof is constructed. Right, so these are all constants depending on the particular functions we have. We needed to keep these constants because later on when we use it, we needed to keep this this sum because later on we're going to need to substitute it for different functions for different charts. Okay, the proof. In the interest of time, I think I'm going to show kind of the essential part of this proof. My notes have more details. I'm going to show part of this proof because this proof is separated out into two parts, two different integral two different bounds. So by triangle inequality, this the term on the left-hand side is bounded by. So we are going to add and subtract z and right. So there are two effects. One effect is to zero in on the set where x is 0, and then the other effect is that you can pull out this leading order term, and you can pull out this leading order term from after you zero in on the 0 set. So this inequality by the triangle inequality, the above is smaller than these two terms. Right, and we are going to discuss just this term. So this term is a different bound, and I think the details in the grade book is very sparse for the first one, and there are several typos, and I think there is a modification needed. We can discuss this afterwards if you are interested. But let's look at this term. All right, so let's write out that term. Z n. So that integral, well, it's equal to the partition function, but you're substituting c naught and phi naught. But we are going to use the same trick as before and try to introduce our density of states integral into into the expression by the property of the Dirac delta distribution. So that's equal to t x to the 2k, y to the 2k prime. And because of the property of the Dirac distribution, whenever we see Whenever we see that, we're going to replace it by t. That's a very hand-wavy way of saying it, but it can be made precise by the property of the Dirac distribution. Okay, so we get that expression. And we are going to invoke a theorem that we have proven before. So theorem 4.6, which is the trick with Main transform and then inverse Main transform. So Main transform give us the zeta function, and then that is particularly easy to evaluate when we have normal crossing, as we do at the moment. And then we inverse Main transform to get the following expression for the density of states that we want. We use that trick to evaluate the dx part of the integral. So we integrate out dx, and that gives us gamma b, which is just some constant, and the n to the lambda falls out of the theorem, and the dt integral goes from 0 to ny to the 2 k prime e to the 2 mod k. So that comes from the fact that that comes from the expression here. And integral of 0 b, so the x has been integrated out. We are left with the y integral. So t to the lambda minus 1 e to the negative b t. So those things, the exponential term are not affected because they only depend on y. I skipped ahead a little bit, so let me not do that. Times. So that inverse Main transform gave us a log term as well. So n to the beta. To the n minus 1 VO0 y. Right. So to bound this expression, and you can see that this y expression is almost isolated from. Yeah.
I lost you there. What's this superscript, which is absolute value of k? What?
So sorry, absolute value of k prime. So k prime are multi-indices, right? So absolute value of multi-indices, just sum them up.
Oh, right. Okay. Sure.
Yeah. So I admit there's a bit of a sleight of hand. So last time I only proved the bounds for the partition function for where the integration domain is 0, 1, not 0 to the b. So I'm a bit cheeky here because so we can derive the same bound from last time with a modification of a constant by change of variable for x to 1 on b to the y. 1 on b times y, and so x becomes x on b and y becomes y on b. That substitution will just modify the constant up the front, and then it introduced this very annoying b to the mod 2k constant up the front. Yeah. Okay. Okay. So if you want to isolate the y, the Linear behavior, we are going to write this log as log n minus log of that remaining b to the 2k, y to the 2k over t term, and that is O to the n minus 1, and we are going to binomial expand this. to isolate leading behaviors. Okay, second board. Okay, so we now have Z of n C V is yep, the equality still holds, is equal to gamma b to the, so I'm going to collect all the n-1 terms, log n to the n-1 terms. So in the binomial expansion, the first term is log n to the n-1. And that's still 2k prime b to the 2 mod k prime dt. Okay. I'm going to write out this one last time. Right. So that's the first term in the binomial expansion with the highest order log n term, and then the rest of the term is collected into so some of the indices from, instead of going from 0 to n-1, it goes from 1 to n-1 of n-1 choose j of the same constant, except now the log n exponent is always decreased by j, which is a non-zero number, and to lambda, and you get the same integral dt, and then you get the dy integral with the same expression, except there is a there is a log. So the second term in the binomial expansion. T. And that's the to the summation variable of the binomial expansion. Okay, right. This term here is almost y, is almost the central part, except the integration domain is not correct. So we are going to split this integration domain from, which is from 0 to n, 0 to this number, into 0 to infinity minus that number. By the way, if anyone is keeping track, this, I should really write this to integral in a different order, because y is the inner integral depends on the value of y. So to infinity, right? And this 0 to infinity integral is exactly the NCV expression that we want, and we just so we have written z as y and cv plus some z1 integral and z2 integral. So it remains to show that these two integral has the asymptotic behavior that we want. Right, so let's go ahead and bound those. Okay, the z1 integral is, so the Z1 integral is just this expression, except the integration is from this number to infinity. So it's always larger than this number. So that is less than, so the constants up the front are not affected. And to handle this term in the exponent there, we will use the same trick we used before, which is mod AB is less than or equal to half a squared plus b squared for any real number, and absorb that into the first term with the penalty of c squared appearing, and then we are going to take just the supremum of that with the penalty of an inequality. So that reduced to e to the beta onto c naught supremum of that. And the same, we're going to do the same trick for just take the supremum of the phi, and so now we are using the boundedness of those two functions. Okay, and that's equal to 0 to infinity. Okay, so right. So the remaining term. So the integration domain is from is bigger than that n y to the 2k b to the 2 mod k prime number, but we are going to integrate from 0 to infinity, but use step function, the Heaviside step function, to enforce that integration domain. And there is a remaining h to 2 lambda k prime there, right? Okay, then this is, if we call this y integral, which is dependent, which is the function of t, v of t, then we note that by the property, by the defining, almost defining property of the Dirac distribution, if we differentiate v prime v, that will give us that changes the Heaviside step function into the Dirac distribution. Okay, dot. And then we are going to use the same theorem we used before, which allow us to integrate the x part, the essential part before, which is looking at the density of states and realizing that it is the inverse Mellin transform of a zeta function that is easy to evaluate because of normal crossing. But then we just need to be careful about which part is essential right now, because we don't have x coordinates anymore. We only have y's. But then even among the y's, they are h prime minus 1 over 2k prime that is the lowest. So just call those the essential coordinates, and then look at their RLCT in a sense. So calculate that, calculate the minimum, and calculate the multiplicity. Give them some name. Then we know that we know, and then we have an expression from this for this integral in terms of t to the t on n to the sum delta, which is our new RRCT, times log n b to the 2k over t to the to some other multiplicity. Let's call that L minus 1. Right. And then to get a bound on V itself, not just its derivative, we just use the fundamental theorem of calculus and integrate it, express V of t as an integration of its derivative, and integrate by parts, give us this bound. The important part is we get an n to the negative delta out. By the way, this bound here changed to S with a penalty of inequality. Details to be worked out, right? So the important thing is the n to the negative delta comes out, and which means that this integral can be bounded by log n minus 1 n to the lambda plus delta, which is a non-zero number, and then copy down the same thing. Okay, that's our first bound. Okay, in the interest of time, I'm going to. Is it okay, Dan, if I skip the Z2 bound? It's really easy.
Yeah, sure. Whatever you think's best.
Okay. So let's move to the next board, and so assume that so once we bound the Z2 bound, we get a theorem, which is the central part for the partition, the singular integral. Okay, the next part is theorem 6.5 in the gray book, and it's basically reiterating a lot of things, a lot of results that we have seen before, but now done in local charts. So we are going to use resolution of singularity and then use partition of unity to partition out our compact parameter space. But here's we make new assumptions. So assume that W is semi-analytic. Our parameter space analytic. And that means that W is cut out by a finite set of real analytic functions. So W is equal to points in our D such that pi j's x are greater than 0 for j equal to 1 to some p, where the pi j's are real analytic on on some open set of R to the D. And we also need our prior to be near analytic. And that means that it has it can be factorized out into a smooth part and an analytic part. So smooth and greater than 0, and that's greater than or equal to 0 and analytic. I will push the discussion of this to the end. So the theorem says that under this assumption, together with fundamental condition 1 before, we can, for any epsilon greater than 0, we can simultaneously resolve the k function that we needed to resolve, and we resolve the analytic part of our prior, and the boundary defining functions for W epsilon, which are the following. So these are, so this is the boundary defining functions for W, and together with this, this is boundary defining function for W epsilon, right? Because K is itself analytic, as we have assumed. So we simultaneously resolve this this series of functions, and we get a resolution M resolving W epsilon, and then M is covered by a finite set of local charts M alpha of the form 0b to the d. So the justification for this is that every point P in the analytic manifold has a neighborhood of negative, has a chart of the form negative b to the d, and then that can be decomposed into a union of charts of the form 0b to the d. So there's say in 2D there are 1, 2, 3, 4 1, 2, 3, 4 parts that 1, 2, 3, 4 quadrants. In 3D there are 8. So there are 2 to the d number of these things. So and we do this for each point in the chart, and that becomes an open cover. And by compactness, we have a subcover, and that subcover can be decomposed into 2 to the d such chart, and that's how we get our M alphas. So this is kind of a justification level. This is not a proof, and I think this is where we require semi-analytic city of W, because I think this can only so this construction is only justified at near the boundary if W is semi-analytic. So this is a remaining unsolved question.
Where does the fact that we've resolved the pies really enter into things, though?
That's my question. that is exactly what's my problem with this. I think the justification.
I think it has to be. I mean, if you allow me to draw on the board briefly, I think somehow we have these coordinate charts in which we're doing these arguments, and this is something like this one up here is all these coordinates u greater than or equal to 0.
Yep.
And in our head, we kind of want to think of the boundary as being something like, oh well, I just chopped this off or something, right?
Yeah, I think this argument here. Sorry, go on.
I was just going to say that if we resolve the pies, then indeed we can basically just assume that picture is true, I guess, right? It means that the boundary just fits into this kind of description very neatly. So being at the boundary just means that instead of having another side to one of those coordinates, you just have something like this, which I suppose is what you're about to point out, which is a very...
exactly.
And then the boundary is not a big deal. It's just kind of where one of these things happens to not have another side, and it's not an issue, and the proof probably doesn't really care.
Yeah, so I think I'm going to keep going with the result, and I think there is one point where the proof should care about this.
Good.
Yeah. Okay. Yeah. So basically, that is also my intuition of where. So basically, this open set does not happen on the boundary.
Right.
Yeah. And that is a gap in logic in the discussion of this theorem. Okay, and the remaining of this theorem just say that in each chart M alphas we have the normal crossing that we need, and then we can and then we are going to call charts where the coordinates of the u to the 2k's and the h multi-indices that attain the minimum, the global minimum, the RLCT, the global RLCT to be the essential coordinates. Okay. I am going to use the next board to hopefully finish up collecting all the results together and finish up the proof. So this is theorem 6.7. And it says that if we collect all the results we have before, we can prove the following convergence in law of random variables. So alpha star is going to be all the essential charts, meaning their multi-indices k and h obtain the minimum possible lambda RCT, so which is meaning the global RCT. Then we have a convergence. So if we factorize out the leading order behavior, the remaining parts converge to a random variable. Right. And the C naught and phi naught are defined in the same way. So those are that, where x and y's are the x and y together consist of u, make u, and x is the essential part, y is the non-essential part. So the proof is that, so we are going to divide the integral of z out into two parts, which is a part in W epsilon, the part close to the zero set, and the part away from the zero set. Thanks for erasing that, Ben, or someone. Right. So we are going to first see that as n goes to infinity, this part is irrelevant. So let's do that. So in k of w greater than epsilon, we can use so by definition of the Cn random variable we had before, this is by definition of Cn. By the way, I think this is a typo in the gray book if you are reading it. the root n is omitted. And by the same trick about AB is less than or equal to half A squared B squared. Again, or Cauchy-Schwarz, you can derive this inequality. And because KOW is always greater than epsilon, we can replace K with epsilon with a penalty over inequality and make the negative term even more negative. Right, and the crucial thing in this argument is that this term, we know that Cn converges to C in law as long as we are away from the zero set, and furthermore by Glivenko, Cantali, we know that this convergence is actually uniform. So meaning the sup over in the whole domain of this converges as a random variable, right? So we have so for the Z1, sorry, let's call that Z1. Actually, to make consistent, that is actually Z2. For the Z2n integral, that is, if you substitute these terms into the expression there, you get so e to the negative beta n beta epsilon over 2 times e to the beta over 2 supremum of the Cn squared. Okay, so that converges in probability to 0 because this term, this term kills everything else because everything else converges to a random variable. And e to the negative n is greater than n to the lambda is greater than that term. Right, so this term is irrelevant. So what's relevant is the first term. Let's go back to the first board and finish up. And okay, the first integral is equal to sum over alpha. So the first integral is the everything less than is in W epsilon. So everything where k is less than or equal to epsilon. And we have from the previous theorem we have shown that that can be resolved, and in local coordinates that become this expression. Right, and we are going to isolate the essential charts as was the idea before, and to define that as and factor out the leading behavior as well. And that's equal to, well, the expression about the essential part of the singular integral we have before. But for each local chart. And I think this is where the semi-analyticity is needed, because to be able to write this for every local chart, some of the charts actually hits the boundary, right? And these expressions we have been using are valid for all kinds for all the local chart that looks like that. Sorry, to the D, essentially. Actually, these are essential coordinates, so we do need them to factor into that. To the S, and I think what remains concerning is what happened when the zero set sort of intersects the boundary, and coordinate charts that intersect the boundary are essential coordinate charts, and I think that's where semi-analyticity is needed. But anyway, that's equal to this expression. So So why this expression here also?
You say it's needed. You say it's needed, and I agree. But do you think there's a gap here, or it's fine?
I'm not sure. In my list of discussion items, it seems like so. In between these two theorems that I'm proving here, in the gray book, there's actually another theorem, theorem 6.6, that shows that if W is semi-analytic, then the zeta function can be continued to a meromorphic function, and that is very much parallel to Atiyah's division of distribution proof, and in that the semi-analyticity is also assumed, and it's used in some essential way. So I think there is a gap, but I don't know what that is. So for now, for this theorem, for what I'm writing here, so we have to have the extra assumption that W0 is not intersecting the boundary.
Mm-hmm. Sure.
Yeah.
Okay.
So recall that Y also have this term. So this cancel out the log n to the n-1 divided by n to the lambda term. And that's the remaining term for Y. I'm not going to write it out. So we are going to use the theorem that we have proven earlier, which is just isolating out the central part of Y, and that showed that in every local chart, so
just to clarify, so you would be safe if W0 doesn't meet the boundary at all, but all you really need is that no essential coordinate has its sort of 0 point at the boundary, right? I mean, as long as the essential coordinates are away, you don't care about the others. Is that right?
I think I'm still a bit wary about that, because what could happen is that the boundary defining function itself. So in the Atiyah's proof, in the Atiyah's proof, we have kw to the s times the characteristic function of W extends meromorphically. The thing is that this thing can contribute u to the k, u to the some other multi-indices, and that might make it into an essential coordinate, like, right? So because previously we have been defining essential coordinates purely based on behavior, the normal crossing form of k only. So this interaction concerns me.
Yeah. Okay.
Yeah.
Wild. All right.
Yeah. So so the theorem 4.9 says that we can everything after dividing out the leading term, there is still a 1 on log n remaining, and so that those are sum over essential charts, and we are going to put the constants that we have derived before into this and stare at them. Nope. Multiplied by v plus gradient of that plus that. Okay, so in all of this, the sigma of the partition unity can be disregarded by another inequality, because you can just take the soup over the finite set of charts, and Cn converges to a Gaussian process on all of M. So it converges to a random variable. Hence, this whole thing converges to a random variable, and hence this converges to 0 in probability. Actually, converges to 0 in probability because the log n kills everything. And yeah, I'm going to say yeah, and therefore Zn naught converges converges to the essential part, to the Z1 part, and converges to that time y of c. So there's another important information in here, which is y is continuous in terms of a continuous as a function between function space with respect to a supremum norm, and hence convergence, weak convergence, so convergence in law is preserved by continuous function. So we can take the limit inside and replace Cn with C here. And that proves the theorem. And then taking log gives us the main formula too. Sorry, I'm massively over time.
Don't apologize. That was great. Thank you. Right.
So there are some remaining things to discuss, which is why I said before, like where and how semi-analyticity of W is used. So before, we only assume W is compact, so it can actually be lower dimensional, but clearly that's forbidden, because we needed to extend the f function to a holomorphic function on an open set in C to the D. So the dimension is not dropping there. And then we need to I still need to understand why the meromorphic continuation of zeta is required, and that's intimately connected to Atiyah's paper.
Sorry, say that again.
Sorry, so theorem 6.6, which is a theorem that Watanabe proved between these last two theorems that I proved. I don't know why it is required. It seems to me that it is not required, but so that proved that theorem says that the zeta function analytic continues to a meromorphic function on all of C. And so by the way, let me write that function that in a way. So zeta of z is equal to integration over all of r to the d k of w to the z times the boundary times the characteristic function of w, and that's where it reduced to integration to over w times the phi of w dw, right? So the content of that function is that this thing, by Atiyah's theorem, this thing analytically continues to a meromorphic function, and then this thing can be Taylor expanded and we can isolate the constant order term, and that preserve the RLCT. That so you have u to the so you have u to the 2k times u to the h times some constant term. Right. And this whole thing, therefore, this whole thing analytic continues to a meromorphic function. I don't know why that is needed in the proof for the free energy formula, and I don't know how the this characteristic the poles of that characteristic function could affect our proof.
Yeah, it's very hard to understand, because why should the function itself matter at all, right? I mean, clearly the set of zeros of gamma, or the places where it's greater than or equal to 0, I mean, it's suppose my gamma is well, I don't know, x cubed, x to the 5th, x to the 7th, or something, so that that series of functions will cut out the same set if I ask them to be non-negative.
Right.
But the higher powers are more singular, so if they were to enter into this calculation, I suppose each one of them should have a different effect, naively. But I don't know, when I'm defining W, I don't care which one I pick, it's just a set, right? So suddenly W is a variety, that is W with these defining equations, matters suddenly for some reason that I don't understand. So, I mean, in many places here, I could swap out one set of analytic functions to define W with any other set, right?
Yep.
But then somewhere I'm not allowed to do that anymore. I find this very hard to tell where suddenly it matters that I'm considering W not as just a set, but really as a variety, a semi-analytic variety in its own right.
Yeah. Also, there is remark. What is it again? Remark 6.6 that justify why we need the pies, the boundary defining function, and also justify why we need the prior to be near analytic, and it's about the behavior of the zeta function, like it might become essential singularity, or it has no poles, and I don't understand. So I don't understand that remark at all. So clearly, some thoughts has been omitted in
I suppose
giving
it must
the fundamental question too.
Yeah. I suppose it must be somehow that just writing the integral sign over W is something too naive, right?
Yeah, I think so.
And that what we actually always mean is this thing you just wrote down, or some variant of it, where we integrate over all of RD, and then there's the characteristic function. But
yeah. So last week I say that last week I make a remark about the history of the discovery of these theorems, and Atiyah did have the division of like the f of x, f of u becomes a of u and u to the k inside in his paper, and it is quite the parallel between the meromorphic continuation of k to the z gamma with the zeta function in singular learning theory is quite striking. So I think the idea come from there. I know that there's like previously there's like the Bernstein-Sato polynomial argument that give us the RLCT, but this seems to be another direction for proof. So I think I need to look at the RTS paper much more closely to see where this is